We will start the second talk. Our speaker is Dr. Brivio of ACTS. The title of this talk is Invariance of Plurigenera in Positive and Mixed Characteristics. Please start.
Thank you very much for the introduction, and thank you very much for the possibility of speaking at the seminar. So today I'm going to talk a bit about the problem of invariance of plurigenera in positive and mixed characteristics. And before I start, let me mention that part of what I'm going to say is based on a joint work with Fabio Bernasconi of EPFL and Liam Stigand of Imperial College. All right, and please feel free to interrupt me and ask questions at any time if I'm not clear enough. So there will be 3 parts to the talk. So I'll start by giving a brief introduction to the problem and an overview of known results in characteristic 0 and characteristic P or mixed. In the second part, I want to give an example of some pathological behavior in positive and mixed characteristic. And in the last part, I would like to explain how the same ideas that lead us to the construction of such pathological examples can actually be used to prove some positive results. And I'll be focusing on the case of families of varieties of general type and families of pairs of corollary dimension 1. And time permitting, which should be the case, I also give a small application of these results. All right, so let me start by setting up a bit of notation. I will denote by U an affine regular one-dimensional scheme. So this guy will always be the base of some projective family of varieties. I will denote by R with maximal ideal M a discrete valuation ring, and big K and small k will be the fraction field and residue field respectively. And throughout the talk, I will assume that the residue field has always characteristic P, positive, and it's perfect. This is not strictly necessary, as some results will hold also in the absence of this hypothesis, but just to make things simpler, let's assume this from the outset. And since I'll be talking about plurigenera, let me just recall what the definition is. So if you have a pair, and by pair I always mean that the boundary divisor has Q coefficients, then the mth log plurigenus is just the dimension of the space of global section of the round down of mkx plus delta. All right, so the main question that motivates this talk is the following. Which I'm going to refer to as IP, which stands for invariance of plurigenera. Suppose that you have a smooth projective morphism or a smooth projective family of varieties. Then is it true that the plurigenera of the fibers are independent? I mean, that they are constant across the fibers for all M. And equivalently, this can also be stated as an extension problem. So this is the same as asking whenever you have a mth pluricanonical form on a special fiber, is it true that we can always extend it to a m-fold pluricanonical form on the total space? So this is a fairly natural question because in higher dimensional algebraic geometry, a lot of the intrinsic, the geometry of a variety is determined by the canonical Q-linear system. So asking whether this is preserved under deformation is a fairly natural question. Furthermore, it's also a pretty useful result. Indeed, a consequence is that, for example, if you have a family of varieties of general type and you take the relative canonical model, then its formation commutes with a restriction to a fiber. So this kind of property is useful in moduli theory, and indeed, as we will see in a moment, the answer to this question is yes, at least over the complex numbers. And this result has been used to prove several boundedness properties. For example, it plays a role in the proof of boundedness of pluricanonical maps of varieties of general type by Egon and McKernan, and also in the proof of boundedness of canonical and log canonical models by Tsuji and Egon, McKernan, Shu. Of course, these two questions are related. So, as I mentioned, in characteristic 0, complex numbers technically, the answer to IP is yes, and this is a famous theorem of Siu that shows that indeed all plurigenera are invariant for smooth deformation of complex projective manifolds. So a couple of remarks about this theorem. So the proof of this theorem is essentially analytic in nature. So it uses techniques from complex analysis like L2 extension theory and the Osawa-Takegoshi theorem, combined with a clever inductive argument developed by Siu. And in general, we don't have an algebraic proof of this result. However, note that if you just care about the invariance of the first genus, the genus, then this is invariant just because since we are considering a smooth family, or all the fibers are diffeomorphic, and P1 is a Hodge number, so we can conclude by using Hodge decomposition and upper semi-continuity of cohomology. Higher plurigenera, however, do not have such a sort of easier interpretation, and so there are no shortcuts. Although in general we don't have an algebraic proof of Siu's theorem, there are a couple of exceptions. So, for example, Kawamata, shortly after Siu's published his result, showed that in the case of varieties of general type, again over C, it is possible to give an algebraic proof using replacing the L2 techniques by Nadel-like vanishing theorems. And in the process of doing it, he also extends Siu's results to families with canonical singularities, showing in particular that canonical singularities deform. And another sort of exception is that way before these results were known, Nakayama in the 80s showed that over the complex numbers, again, invariance of plurigenera follows from the abundance and the MMP conjectures. Yeah, so, and last, let me just point out that, again, since this is an extension problem, one can hope to use some vanishing theorems to kill the obstruction in H1, provided that Kx has some positivity property. So if one is interested in extending this result to characteristic P, the situation doesn't look so nice, because again, in characteristic P there is no L2 extension theory. Hodge theory behaves kind of funnily. Vanishing theorems are known to fail. So, I mean, one should not expect that everything works out just in the same way. And indeed, it is sort of well known that at least as far as P1 is concerned, the deformation invariance can fail. So the first examples, I think, for elliptic surfaces are given in by Katsura and Ueno in their famous paper about elliptic surfaces in characteristic P. Lang also gives examples of request surfaces in characteristic 2 where P1 jumps. And more recently, Su showed that the same can happen even for general type surfaces. So, and furthermore, this jump can be arbitrarily large. So there's not really a way to control this. So invariance of plurigeneral literally, as stated before, fails because P1 can jump. However, in all of these examples, invariance of plurigenera holds asymptotically. So as soon as M is sufficiently divisible, then invariance of plurigenera actually holds. And so one can ask the following weaker question, which I call asymptotic invariance of plurigenera. So given a smooth projective family of varieties over a DVR, then is it true that the plurigenera of the special and generic fiber are the same when M is divisible enough? And in spite of this being a weaker question, I mean, a weaker property than invariance of plurigenera, in terms of application, this is as good as the other. If you are interested in taking the relative canonical model and being able to say that its formation commutes with restriction to a fiber, then this is as good as invariance of plurigenera. And so there are some partial results towards this. For example, Egbert and Hekon in 2015, they showed that if you have a log-smooth family of surface pairs, which have either Kodaira dimension not equal to 1, or delta small k is big over the canonical over the ample model of the central fiber, then you actually have the formation invariance of asymptotic invariance of log plurigenera. And more recently, me and Bernasconi and Stigant have generalized this result to families of surfaces which are not necessarily log smooth, but we allow for a sort of Ward singularity. The precise statement is a bit technical. And we also allow for a non-perfect residue field, which Egbert and Hekon instead require. But anyways, it's these techniques, the techniques that we use, that Hekon and Egbert used, don't work when the Kodaira dimension is equal to 1. However, they don't give an example in which asymptotic invariance of plurigenera fails. However, such an example exists, and this is what I show. And so, more precisely, I show that there exists a smooth family of Kodaira dimension 1, such that asymptotic invariance of plurigenera fails, and the gap can be arbitrarily large. So, in particular, in positive and mixed characteristic, abundance plus minimal model program don't even imply this weaker version of invariance of plurigenera. Are there any questions up to now? Okay, so if not, then I would now like to give an outline of the construction of this kind of families. So the main idea is the following. Suppose that you have a family of complex minimal surfaces of Kodaira dimension 1. So now we are over C. And suppose that you want to prove invariance of plurigenera for this, or sorry, asymptotic invariance of plurigenera for this family. And so there is a kind of a low-tech approach, which is the following. So since we are in low dimension, let's assume that K of X is actually semi-ample. So we can take the Itaka fibration of Kx, denoted by F from X to C over U, and this is a contraction, right? So the push forward of the structure sheaf is the structure sheaf of the base. Now let's also let's also assume that C is a smooth family of curves over U. These of course follows from invariance of plurigenera, which is the thing that we are trying to prove. There are other arguments which are not completely trivial. For example, one can use fiber space adjunction to prove that a special fiber is normal, but let's not get into the details. You can just assume that this is smooth. So we have a nice family of surfaces fibered over a nice family of curves. And since Kx is semi-ample, you can write it as being Q linearly equivalent to the pullback of an ample Q divisor on C. And okay, so now for any point in U and any M sufficiently divisible integer, you have this sequence of equalities where the first one follows simply by the projection formula. The second one is a consequence of the fact that the push forward of OXU being equal to CU, since we are in characteristic 0 and the bases of these vibrations are normal, by the Zariski-Main theorem, this is equivalent to FU being with connected fibers. And this holds because F is a contraction, so it has connected fibers. And lastly, the equality between H0 and chi is simply because of Serre vanishing. Since we are taking M divisible enough. Okay, but then at this point, we are done because this plurigenus is equivalent to, is equal to this Euler characteristic, which is invariant in smooth families, flat. Okay, so in the complex case, this gives us a proof of asymptotic invariance of plurigenera. So what happens in positive or mixed characteristic? Well, the problem with this argument is in the second equality, because in characteristic P, being a contraction is strictly stronger than being a map with connected fiber. Just think of the Frobenius. And so this is where the argument breaks down. But on the positive side, now we know exactly what is that we need to construct in order to have such a pathological example. So we are trying to find a family of minimal surfaces of Codara dimension 1, such that when I take the relative Ithaka vibration over a spec R, we have the following picture. So when I take the base change over the generic fiber, I got a nice elliptic vibration. So in particular, this is a contraction. Instead, when I look at the reduction modulo M, I have a factorization like so. I have Fk bar, which is an elliptic vibration. So in particular, a contraction again. And then I have the geometric Frobenius. So in other words, what I'm trying to construct is an example in which Stein factorization and reduction mod M do not commute. And so in particular, now you see if something like this happens, you see that this sheaf will just be equal to OC big K when U is equal to the generic point, and instead it will be a rank P vector bundle when U is equal to the special point. So twisting everything by a sufficiently ample line bundle, you will have a jump in plurigenera of the order of P. All right. So let's construct this family. So the construction is, uses fairly standard techniques, but there are a couple of tricks that one needs to use. So first step is constructing a family of elliptic fibrations such that it degenerates to this kind of inseparable fibration in characteristic P. So first, we take an elliptic curve, E over R, so smooth, such that when we look at the specialization map on the p-torsion part of the Picard group, this is not injective. So this is not too hard. There are many examples like this. In mixed characteristic, any elliptic curve will do. And in equicharacteristic P, you can deform an ordinary elliptic curve to a supersingular one. Then we take a line bundle in the kernel of this specialization map. In other words, this guy is p-torsion and well, non-trivial. Non-trivial on the generic fiber and trivial on the special one. And then we take a non-zero section in its mth tensor power. Then we will take P1, which is the base of our elliptic fibration with coordinates S and T, and the hyperplane bundle, and sigma n this section S to the P minus 1 times T in N to the P. And then we take products. So Y is the product of E with P1, L is the product of M with N, sigma L is the product of these two sections, sigma M and sigma N. And now we get the induced p-cyclic cover, V to Y, and we let phi be the natural morphism down to P1. So the picture that we end up with now is the following. This is my map phi. And if I look in the chart where big S is not equal to 0, we have the following picture. Here, psi is just an element of OA star, which is a local trivialization of sigma M. And note, because by the way we chose M, that our psi belongs to small k star modulo M. So on the central fiber, it just becomes a constant. And so, in particular, you see that if you reduce modulo M, the field extension, you can see that the Stein factorization of phi k is non-trivial because you are adding a pth root of T on the central fiber. So this is good because this is the phenomenon that we were looking for. However, we are not yet exactly done. For example, so because of two reasons. So note that in this chart, V is smooth. However, it is not smooth in the other chart. So when you take T not equal to 0, you will see that V actually is not even normal. It has a two-dimensional singular locus along the fiber over the infinity section of P1 over R. However, this is not too big of a deal because you can just normalize. And if you normalize, you find out that you end up with a new family of surfaces, V bar, which is actually a smooth R scheme. There is still another problem. That is, if you look at this new, the generic fiber of this new family, then this is an isotrivial elliptic surface which has multiple fibers over 0 and infinity. So in particular, this has not Kodaira dimension 1. And so the idea now, whenever you have such an elliptic surface, you can always increase its Kodaira dimension by taking a ramified base change, ramified cover of the base. But here, since you're working with a family, you need to be a little bit more careful And so the idea is to base change via a special finite map, which is a sort of Artin-Schreier-ish cover of P1 given by this equation, and then normalize. So let me give you a picture of why do you need to do something like this. So let's say that this is our family V, or V bar, and these are our P1s. So this is over big K, and this is over small k. So, and now we do this base change via this map pi. So now, and let's call this X. Okay, so in our family V bar, the situation is the following. If you take a general fiber over big K, what you get is just a nice smooth elliptic curve. Instead, if you take a general fiber of the elliptic vibration modulo M, since this map factor through the Frobenius of the base, what you get is a sort of a thickened elliptic curve. Also, we know that we have two singular fibers over 0 and over infinity. Now, if you take the base change via this map is étale in a neighborhood of 0. So what you get is that you are increasing the number of singular fibers. When instead the generic fibers are, the general fibers, of course, they remain the same. So you still have a thickened fiber here, thickened elliptic curve, and a nice smooth elliptic curve here. But then if you look at what happens over infinity, you will see that you are getting singularities over at infinity. So you get a singularity on the generic fiber, and you also get a singularity on the special fiber. So, but this is not a problem now, because if you take the normalization turns out will get rid of this singularity all across the family over R. So let me stress out that it's important to take a base change via this morphism, because if you just took any general morphism, what you would end up with would be a picture like the following. So you don't have, you only have singularities on the central fiber. And now this is not very good, because you need to smooth out the family, keeping the generic fiber untouched. And this is not really clear to me if it can be done. So the advantage of creating singularities everywhere is that then the normalization can take care of this. Can desingularize the whole family at the same time. So after normalizing, now you end up with a nice family of surfaces of Kodara dimension 1, and on the central fiber by construction, you still have this non-trivial Stein factorization. Any questions? All right. So before I move on, sorry. Can you see? Hello?
Oh, I can see your screen.
Okay. Sorry about that. Okay, so if there are no questions, let me move on to the next step. So a couple of remarks. as I mentioned before, asymptotic Riemann rock gives us that if you the jumping plurigeneral is of the order of P. However, if you replace P by P to the E, so you start working with the P to the E torsion line bundle instead of P, you get a jump of the order of P to the E. And so in particular, the jumping plurigenera can be arbitrarily large. And of course, another simple remark, taking products, we can get example of this behavior in any dimension and any codata dimension between 1 and the dimension of the variety -1. All right. So now I would like to talk a bit about some sort of positive results instead. So what can you show? What can you prove using this circle of ideas? So the key input is this this lemma that connects Stein factorization and invariance of plurigenera, not even of plurigenera, really invariance of sections of a line bundle. So if you have a flat family of normal projective varieties, and L is a semi-ample line bundle on this family, you can take the semi-ample fibration of this line bundle, and then the fact that the dimensional spaces of sections of L to the M restricted to a fiber is independent of the point you're taking the fiber on for all M sufficiently divisible, is equivalent to the Ithaka fibration commuting with restriction to a fiber. So the proof, we already saw the proof of this. So let me just record it, what's going on. The point is just we can pull back, we can write L as a pullback of an ample divisor from the base, and then projection formula and insert vanishing identify H naught with this chi. And once the Ithaka fibration commutes with restriction to a fiber, we know that this guy here is nothing but OZU, and hence we can conclude easily. All right, so if we want to study invariance of plurigenera for so this is useful for studying invariance of plurigenera, provided that the log canonical divisor in our family is semi-ample, so that we can actually have an Ithaka fibration. I mean, an Ithaka fibration that is a morphism. This is kind of a strong hypothesis. Is basically like assuming MMP and abundance. However, since MMP and abundance in general do not imply invariance of plurigenera, even asymptotically, it's sort of reasonable to make this assumption first and see what one can prove. So in order to give a sufficient condition for this compatibility to happen, we use the following result from deformation theory. So I learned this on a paper of Sink and Van Straten, and they refer it to another paper of Val. Anyway, this should be a fairly well-known result. So it says the following: suppose that T is the spectrum of a local Artinian ring, and suppose that T to T prime is a square zero extension, so a thickening of T. And then let's take F from Y to X to be a morphism of T schemes, which is a contraction and which has vanishing first direct image. And suppose that Y has a lifting Y prime over T prime. So these are lifting means a flat lifting. Then this theorem tells us that we can sort of push down this lifting and obtain a lifting of both X and the morphism F over T prime in such a way that the obtained morphism is still a contraction and it still has a vanishing first direct image. So so I won't prove this theorem, but let me just tell you what is the idea. Note that all the vertical arrows are homeomorphisms. So from the point of view of, I mean, in order to make to give us make sense of X prime as a scheme, we just need to put a suitable sheaf of rings on it. And the point is that one defines the sheaf of rings on X prime just as the push forward via F of the sheaf of rings O Y prime. And then, okay, I mean, if this works, then it's clear that the new morphism, it's a contraction. One needs to check that, for example, with this structure, X prime is a flat T scheme, but one can do this. And so the point is that, and the point that I want to make is that this is the sheaf of rings that X prime comes with. Okay, so one can use this lemma to prove the following sufficient condition for Stein factorization to commute with restriction to a fiber. So let X be a normal projective R scheme with a normal special fiber, and let F be a contraction of R schemes, and suppose that this is the Stein factorization of Fk. So we have F bar K is the contraction part, and Hk is the finite part. And suppose that you have a vanishing first direct image of the contraction part, then Hk is trivial. And the idea of the proof here is just to formally lift the Stein factorization. So, so we have a map Fk here, and we have a map Fk1 here, which is just the one induced at the sort of first order neighborhood of the closed point. Now, if I use the lemma of Sink van Straten, what I obtain is a lifting of zk bar to zk bar 1, and a lifting of fk bar to fk bar 1. So in order to extend this Stein factorization to the first order, I just need to give a map, a morphism like this. And this essentially amounts, since all these four schemes are homeomorphic, to just give a map of rings from OZK1 down to HK push forward of OZ bar K1. But then, if you remember how we defined the ring structure on Z bar K1, this is nothing but the push forward via FK bar of OXK1. And this is just the push forward via FK1 of OXK1. But we already have a natural map here, since we do have a map FK1 between these two schemes. So this is so this gives you the desired map, and so we can live to the first order here. And then one keeps going, you end up taking the limit, and then the point is that since F is a contraction, the Stein factorization, even at the formal level, must be trivial, and if HK is non-trivial, then this cannot happen, so yielding a contradiction. All right, so once we have this criterion, there are a couple of easy corollaries that are still interesting, at least in my opinion. So the first one is that if you have a projective family of terminal good minimal models of general type, such that either the relative dimension is 3 and the residue characteristic is greater than 5, or the canonical model of the central fiber has rational singularities, then asymptotic invariance of plurigenera holds. And well, the second corollary instead is for pairs. So suppose that you have a projective family of pairs which has a Kodaira dimension 1, and again we need to assume that kx plus delta is semi-ample. Here we also need to assume that the central fiber is Gorenstein and locally F-split over the ample model of the central fiber, and delta k, small k, is ample over the ample model of the central fiber. Then it means that then we have that the plurigenera, invariance of log plurigenera holds asymptotically. So about this condition locally F-split, so I don't want to get into the details, but basically this is a relative version of the notion of F-splitting, which simply means that the map of rings induced by the Frobenius morphism splits, and this is formulated in terms of the relative Frobenius. So combined with this delta k being ample, this just means that if you look at the map xk to this proj, what I'm basically saying is that this is a arithmetically nice family of Fano varieties, very, very roughly speaking. All right, so the proof of this is now follows more or less quickly from the previous theorem. This is because we can just take the Ithaka fibration of kx plus kxk or kx plus delta k, and it is enough to show that this has vanishing direct image. So in the case of in the general type case, this follows essentially by the definition of rational singularities. And in particular, when the dimension is 3 and the residue characteristic is greater than 5, canonical singularities are always rational. Actually, KLT singularities are always rational. And this is by a result of Arvinson, Bernasconi, and Lacini. And instead, in the second case, since the morphism is, since the Ithaka fibration phi is locally F-split, one can actually show a relative Kodaira vanishing for this kind of morphism, basically mimicking the fact that for F-split varieties, the Kodaira vanishing theorem holds, and so conclude the vanishing of the first direct image. All right, and I just want to mention a last application of the first corollary, which is I mean, I should say this is still a work in progress, but one can prove boundedness of certain canonical models of dimension 3 over an algebraically closed field of characteristic greater than 5. So, and these canonical models have to be either irregular or have a Gorenstein terminalization. And the idea of the proof is basically mimics Tsuji's idea for boundedness of canonical models in characteristic 0. So the proof goes like this. By a result of Zhang, we know that for m greater or equal than 43, the pluricanonical linear system nkx induces a birational map. So this can be used to show that the class CV is birationally bounded. So you have a morphism of schemes of finite type such that every class in CV, every element in CV appears as a is birational to a fiber of this morphism. Now, in characteristic zero, now what one usually does is sort of after shrinking S, one can assume that this family is a smooth family of varieties of general type. The idea is similar, but the point is that one has to work FPPF locally, which is just a fancy way of saying that one cannot just shrink S, but one also needs to take possibly some purely inseparable cover of the base in order to apply this kind of reasoning. So, but anyways, if you allow for this, then you can assume that Y is a smooth family of varieties of general type. And after possibly shrinking further S, you can actually run an MMP, which terminates with a good minimal model, which is also a fiber-wise good minimal model. So for every small s in S, the induced map rho S is a minimal model of the fiber y small s. So this is due to results of Das and Waldron that show that MMP for three-folds over imperfect fields. And now you have a family of varieties where the canonical divisor is semi-ample, so you can apply our results about asymptotic invariance of plurigenera and take the relative canonical model, which will then be a family of canonical models. And then one conclude by simply stratifying S, possibly FPPF with FPPF opens, but then the argument is essentially the same as in characteristic zero. So I think I'm a bit early, but I'll end it here, and thank you for your attention.
Okay, thank you for your nice talk. Any question or comment?
Excuse me.
Yes.
Is Godard dimension invariant?
So good question. So I mostly assume that the families that I'm working with are semi-ample. And in that case, Godard dimension, yes, is invariant. In general, it is not known. So even for like smooth family of varieties in characteristic P or mixed, it's not known whether Godard dimension is invariant in dimension, say, greater than 2, relative dimension greater than 2.
Thank you very much.
You're welcome.
Any other questions? Okay, yeah. Thank you for our speakers and every participant. So today's seminar is finished. Thank you.